Welcome back. This will be a short introduction to Section 3.1, Sampling Distributions. I've divided the section up into three subsections: statistical inference, sampling distributions, random sampling, and then a summary of the section. Let's begin with statistical inference. Very often we're interested in a quantity that exists within a population. For example, what is the proportion of the population of France that's retired? Or, for example, what is the mean annual income of the workers within the United States of America? Oftentimes these populations are very large, and it would be difficult to get our hands on these quantities in and of themselves. Instead, we resort to collecting a sample. We do some data collection. We can compute that quantity within the sample and then impute that quantity to the entire population. This is a process that's called statistical inference. So statistical inference is the process of drawing conclusions about the entire population based on information within a sample. Now, it's important when working with populations and samples to get some terminology straightened out and correct. So a parameter is a number that describes some aspect of a population, whereas a statistic is a number that is computed from the data in a sample. We think of our sample statistic as our best estimate of the parameter of interest. So if we want to calculate a parameter within a population, we think of our parameter of interest as being approximately equal to our best estimate. It is often the case that our best estimate coming from the sample will not equal the parameter of interest, but we hope that our best estimate is approximately equal to the parameter of interest. For the same quantity, we will use different notation depending upon whether that quantity is being measured within the population or within a sample. So the same quantity will have one representation as a parameter and another representation as a statistic. For example, we'll use mu and x bar to denote a mean, one within the population and one within the statistic. Likewise, the standard deviation will be denoted by sigma or s, the proportion by p or p hat, the correlation by rho and r. Let's take a look at an example. Of an Academy Award, an Olympic medal, or the Nobel Prize, what proportion of college students prefer the Olympic medal? Results of a student survey are shown below. Let's look at three questions. What is the population under consideration? What is the population parameter to be investigated? And finally, what is the best estimate for this parameter from the survey data? We'll go to the overhead camera and work out the answers to each of these questions. So please join me over at the overhead camera. All right, welcome to the document camera. Let's work this problem together. Of an Academy Award, an Olympic medal, or the Nobel Prize, what proportion of college students prefer the Olympic medal? Results of a student survey are shown below. All right, let's answer these questions. What is the population under consideration? Well, if we go back and look at the question, it's pretty clear we're trying to get information about college students. And so the population under consideration is just the population of college students. Okay. What is the population parameter to be investigated? Well, it's a proportion. So we're going to notate that by P. And what is P equal to? It's the proportion of college students, or we could say of the population, it's the proportion of college students that prefer the Olympic medal. Okay. And what is the best estimate for this parameter from the survey data? Well, when we look at the survey data, we can see that of the 362 people that were surveyed, A lot of them, right? Nearly half of them, 182 of them, would prefer the Olympic medal. And so that gives us a proportion within the sample of 0.503. Now, P is the proper notation for the parameter, but for the sample, for the statistic, we're going to use P hat. Of course, it's our hope that this P hat, given a large sample like this, it is our hope that P hat is very close to the value of P that we're interested in. So this is what we're really interested in. This is what we actually can calculate, and what we're hoping by inference is that that value of P is very close to 0.503. And that's the idea. All right, let's go back to the class notes. Let's look at one more problem of this type together. What is the correlation between the pH and mercury levels in the fish in the lakes in Florida? Results of a sample are given below. What is the population under consideration? What is the population parameter to be investigated? And what is the best estimate for this parameter from the survey data? Again, we'll look at this problem. We'll work this problem together under the overhead camera. Let's make sure that in all of these cases we're using proper notation. So I'll meet you over at the overhead camera for the solution to this problem. All right, so welcome to the document camera. Let's work this problem together. What is the correlation between the pH and mercury levels in the fish in the lakes of Florida? Results of a sample are given below. And so we can see our summary of our sample statistics here. But let's go through these questions one at a time. What is the population under consideration? Well, by reading the question again, we can see that this is pertaining to the lakes of Florida. So whatever this study is trying to do, it's trying to study all of the lakes of Florida through this sample. So we're going to say that the population under consideration is consisting of the lakes of Florida, the Sunshine State. All right, so what is the population parameter to be investigated? Well, the population parameter to be investigated is a correlation. When we're working within a population, the parameter would be notated by rho for a correlation. And we're going to say that it's the correlation between what? The pH and mercury levels. So rho is the correlation between pH and mercury levels. Okay, now what do? We pull a sample. We grab a sample of 53 lakes in Florida. We find their pH and mercury levels. We form the scatter plot. We've looked at this data before. And what we can do is from this scatter plot, we can find what's called the sample correlation, and we can find that number right here. The sample correlation is negative 0.575. So our best estimate for this parameter rho is what we would call a sample correlation notated by R, and it is negative 0.575. We could use this to estimate that. That's the idea. Okay? All right, so that brings this problem to a conclusion. I'll join you back at the class notes. So here are a few questions that we should have in our minds as we finish this first subsection. So statistical inference operates under the assumption that your best estimate is a good approximation for the parameter of interest. So question 1, how good is this approximation? And question 2, how are we supposed to answer question 1 when we don't know the value of the parameter? How are we supposed to know that our best estimate is a good and faithful approximation of the parameter of interest when the parameter of interest is essentially unknowable to us? So those are some of the topics and some of the questions that we hope we'll answer by the time we leave this section. This leads us to our next topic, sampling distributions. So what is a sampling distribution? A sampling distribution is the distribution of sample statistics computed for different samples of the same size from the same population. A sampling distribution shows us how the sample statistic varies from sample to sample. So the idea is something like this. Suppose we draw a sample of size 50 out of a population to measure some proportion. Well, each time we pull a sample of size 50 out of that population, we are likely to get a different proportion. And so a sampling distribution acknowledges the fact that that proportion is not a fixed entity, but it is going to be different from sample to sample. And so the sampling distribution shows us the variety of possible proportions that we can see coming from that population. Let's take a look at this in an example. To understand this example, you have to imagine some parent population. There's some quantity within that population that we're interested in. We're interested in the mean of that quantity. Now, what are we doing? Repeatedly, we're pulling out samples of size 10 from this population, and we're computing the mean within the sample. We're computing an X bar. We do this 300 times, and each and every time we record the value of X bar. And then we take those recorded values for X bar and we plot them in a dot plot. So what you're seeing here is the result of carrying out this experiment 300 times. Each and every one of these dots in this diagram represents a different value of X bar, a value of X bar that we saw from a particular sample. So what you're seeing here is that in fact, there's a lot of variety in the different values of X bar that we saw. We saw values of X bar that are as low as maybe 21 and as high as 63 or nearly so. So we don't expect the values of X bar to be the same every time. In fact, what the sampling distribution is showing us is that there's a lot of variety in the values of X bar that we will see. Now, this dot plot was produced by StatKey, and we'll be doing some of these later in the lecture. But for now, let's realize that StatKey always provides some vital information about the dot plot up here. Let's take a look. The first piece of information that we're given is how many times a sample was withdrawn from the population. And what this is telling us is that this was done 300 times. So 300 samples corresponds to 300 different dots within our dot plot. The second piece of information is giving us the mean of the dots themselves, and is telling us that the mean is at 41.943. Now, StatKey always shows us this value on the x-axis, and you can see that there are going to be some dots to the left, there are going to be some dots to the right, but on average, the value of the dots is 41.943. The final piece of information that StatKey gives us is the standard error. Now, what is that? That's the standard deviation of the dots in the dot plot, right? And it's telling us that the standard error is 9.039. All right, now, let's see if we can make sense out of that standard error. Let's recall something that we had learned earlier, right? If I wanted to carve out the middle 95% of these dots, we would know that that's going to leave 5% out, and 5% of 300 is 15. Now, half of those dots have to come from the left, and half of those dots have to come from the right, and just to keep things simple, let's carve out the top 8 and the lowest 8. Now, I did that work. If you count down from the top, you'll see that that red dot there, these are the top 8 dots. And if you see this red dot here on the left, these are the lowest 8 dots. Let's imagine pulling those out of the dot plot. So we're carving out the highest 2.5% and the lowest 2.5%. What's left is the middle 95%. And our theory tells us, right, that that has to encompass 4 standard deviations. Now that's a range from approximately 25 to 60. Now, just to make the math easy, let's make that range from 24 to 60. That's a range of 36 that has to be spanned by 4 standard deviations, and that means the standard deviation will be 36 divided by 4, or 9. So we can connect this standard deviation that we're seeing up here, this standard error, with our notion of standard deviation for this dot plot. Okay, now let's talk briefly about accuracy and precision in this method. Now, To say our method is accurate, what we're hoping is that even though our dots are sometimes straying to the left and sometimes straying to the right, we're going to say our method is accurate if this mean value, this 41.943, is close to or is accurately predicting the parameter within the population. So it is our hope that our method is accurate in the sense that even though our dots are off to the left or off to the right, on average, they are going to be producing something close to the parameter within the population. To talk about the precision of our procedure or the precision of our method, we're really talking about how much variety we're seeing here within our dot plot. So the closer these dots are packed around the average value, in other words, the smaller the standard error, the more precise our procedure is. Okay, so we're going to be kind of coming back to these ideas again and again and again, but the accuracy of our procedure is reflected in this mean, and the precision of our procedure is being measured in this standard error. We'll have a lot more to say about that as we work our way through this chapter. Now, these last 2 points bear repeating. For the parameters we will consider, if samples are randomly selected and the sample size is large enough, the sampling distribution will be symmetric and bell-shaped and centered at the value of the population parameter. In other words, our best estimate is accurate. The standard error of a statistic, denoted by standard error or SE, is the standard deviation of the sample statistic. It's the standard deviation that we see in our dot plot. As the SE of a test statistic decreases, the precision of a test statistic increases. Now, before we leave sampling distributions, I want us to work a couple of problems just to show you how StatKey implement sampling distributions, and I hope that by the time we're done working these 2 problems, you'll have a much richer understanding of how sampling distributions work. So let's go ahead and take a look at a problem that we'll work through. We're going to load StatKey. We're going to go to sampling distributions, mean, percent with internet access, parentheses, countries. Now that is the default file, so we'll see that we don't have to do anything to load that file in particular. Okay. We're going to look at the population that's under consideration. We're going to ask, what is the shape of the data set and what is the mean parameter for this population? We'll see how to read that information right out of StatKey. Now, we're going to set the sample size at n equals 10. Now, that's going to be particularly easy because that is the default. So we're going to just notice that the default is set for n equals 10. And we're going to generate some samples one at a time. This will get you comfortable with what the procedure is that StatKey is invoking. And then, once we understand the mechanics of this procedure, we'll just have StatKey sample thousands of times for us. And then we're going to come back and we're going to answer 5 questions that deal with those thousands of samples that we generated. And then we're going to basically redo question 4 by resetting the sample size to n equals 40, and we're going to ask, what changes do we expect to see, and what did we actually see? So this will give us a chance to kind of anticipate what's going to happen if we, instead of taking samples of size 10, we allow ourselves to take samples of size 40. What changes do we expect to see in our answers for questions 5.1 through 5.5? Okay, so let's not tarry any longer. Let's go over to StatKey, load the file, and begin to kind of plow our way through these questions. Okay, let's go to StatKey. We'll be working in a new region of StatKey, and now we're working with sampling distributions, and in particular, the mean. The file we're interested in is percent with internet access, countries, and you can see that that is the default file for sampling distribution for a mean. So we're all set there. Now let's take a look at the file. Over here on the right, you can see the population, the set of gold dots. Each one of those dots represents a country, and each country was asked to report the percent of the population that had internet access. So you can see there are many countries over here on the low end which have very little internet coverage, and then we have some countries on the high end here where almost everybody in the population has internet access. We can see the mean is 43.024. Now, what we're going to be interested in doing is selecting samples from this parent population. The size of the sample is set here. Choose samples of size n equals. The default is 10. That, of course, I can click on that button and change that to anything that's reasonable. Okay, let's go ahead and just see what happens when we start generating samples. So I can generate samples one at a time by just saying generate one sample. Okay, what's happened here is that 10 of these dots have been selected at random. They get dropped down here into this window, and the mean of this collection is computed, in this case 38.26, and that 38.26 is plotted over here in this main panel. Okay, if I generate another sample, 10 new dots are drawn. They're plopped down here in this lower window. Their mean is computed, and now I get the mean of the original sample and the mean of the second sample. And what we're seeing here, this 42.605 down here, this represents the mean of those two dots. Okay, so each time I generate another sample, a fresh set of dots is being selected, the mean is being computed, a new dot is being added to the array, and the mean of the collection is being computed. Okay, so we can see already by having generated 3 samples that we're getting these mean values for the samples. They're kind of ranging all over the place, but collectively they have a mean of 42.683. Now, this is a fairly automatic process. It's something that's very easy for the computer to do. It simply selects 10 dots, brings them down, computes the mean, plots the dot, updates the mean of the entire dot plot. So what we're interested in doing is not generating these samples one at a time, but generating these samples 1,000 at a time. We want to build up a very large dot plot consisting of several thousand samples, so we can kind of see a range of all the possible samples that could be drawn from this population. Okay, so let's take a look at that next. What I want to do is reset the plot, and now I want to use the generate 1,000 samples button repeatedly. So what I want to do is come up here and hit this button. Now 1,000 samples have been selected. That process has gone on 1,000 times. I can do it again. I'm up to 2,000, 3,000, 4,000, 5,000. You can see that the number of samples here is now up to 5,000. So I've done this procedure of selecting 10 dots, computing their mean, throwing a dot into the dot plot here. I've done that process 5,000 times now. Okay, let's take a look at some of these questions that we were asked to think about, right? So generate several thousand samples. We've done that. What is the shape of the dot plot? Well, we can easily see that the shape of this dot plot is bell-shaped. We would identify that as a bell-shaped dot plot. What is the mean of the dot plot? The mean of the dot plot is now 43.141. And I'm going to want to write that down so that I can use that piece of information later. So right now the dot plot is averaging 43.141. Now, I do want to point out while we're looking at this that coincides very nicely with the mean of the population itself. This is a testimony to the fact that this procedure is an accurate procedure. Even though any particular dot in our dot plot may not be very close to the mean of 43.024, our entire collection of samples is hovering around the correct mean of 43.141. So this is an accurate method. Okay. What is the standard error of the dot plot? We can get that right here. The standard error is 9.052. I'm going to write that down as well. Okay, so we've got the mean and the standard error. All right, what is the range of the middle 95% of the data? Let me show you this. This can be done in a couple of different ways. The first way we're going to do it is just to have stat key literally count. I'm going to click on two tails, and what stat key does is it simply carves out the leftmost 2.5% of the population and the rightmost 2.5% of the population, and those are drawn in red, and you can see the statistics here. That represents 2.5% of the dots on the right, and this represents 2.5% of the dots on the left. The dots that are drawn in black are the middle 95% of the dots in the array, and we can see down here that that ranges from 25.635. I'm going to write that down for comparison purposes. That ranges from 25.635 to 60.915. And so what we're saying is that this interval from 25.635 to 60.915 carries 95% of the dots that are generated. All right, 5% of the dots will fall outside of that window. All right, method number 2. Compute the range for the middle 95% of the data from the formula mean plus or minus 2 standard errors. How does this compare with the previous calculation? Let's take a look. So now I want to clear this so I'm not confused by that. And now I need to go and do a calculation using I'm going to use the Desmos scientific calculator. I need to take the mean that we found, which was 43.141, and I need to add to that 2 times the standard error, which was 9.052. That's going to give me a right endpoint of 61.245. I'm going to write that down. I'm going to open up another calculating window here. I'm going to take the same calculation, and this time I'm going to change out that plus sign for a minus sign, and that's 25.037. Okay. So again, for the purposes of comparison, when I had stat key do the middle 95, it went from 25.635 to 60.915. When I did the calculation using mean plus or minus 2 standard errors, I got 25.037 for my left endpoint, and I got 61.245 for my right endpoint. So you can see, just by working with the mean and the standard error, right, not having to count dots at all, just working with the mean and the standard error, I get a pretty good idea about the window or the interval that contains the middle 95% of the data. All right? Now what we want to do, let's go back here. What we're going to want to do now is redo this entire question 4, now choosing samples of size n equals 40. And the question that you should think about before we get into this is, what changes do we expect? How different do we expect the situation to be? Well, let's find out. So we'll go back to StatKey, and we're going to get a fresh start. I'll reset the plot, and now I want to change the n equals 10 to n equals 40. I want to choose samples of size 40. Just to make sure we understand the difference now, when I generate one sample, I am now pulling 40 dots down from above, and I am collecting those 40 dots together into a sample, computing the mean of the sample, and plotting that dot. So if you think about it, each time I draw a sample, I now have a sample that's of size 40 as opposed to size 10. I've increased the amount of information in my sample by a factor of 4. Okay, let me reset the plot, because what we're really interested in doing is generating thousands of samples at a time. So we're going to generate the same as before, 5,000 samples. Okay, now let's take a look at the difference. The plot appears to have exactly the same shape. What is the shape of the dot plot? It's bell-shaped. Okay. What is the mean of the dot plot? Well, it's nearly the same, right? Our dot plot is still centered on a number that's roughly 43, which reflects the mean of that parent population. So my dot plot is still centered on exactly that same axis as the previous dot plot. All right, here's where we're going to see the difference, though. What is the standard error of the dot plot? When I go to check the standard error, I can see that it is now 34.217. I'm going to write that down for purposes of some of our later computations. So we can see that our standard error is smaller, significantly smaller, about half as big as it was before. We had a standard error on the order of 9 when we chose samples of size 10. We've increased our sample size by a factor of 4, and we've cut our standard error down by nearly a factor of 2. Okay, so if we were to lay the old dot plot, the dot plot from samples of size 10 on top of this dot plot, samples of size 40, this would be much more tightly packed around this mean value of 43.02. We'll see that quantified in just a second. Okay, next question. What is the range of the middle 95% of the data? Well, let's do it by method 1, literally having stat key count for us. Our middle 95 now goes from 34.520 on the left out to 51.271 on the right. Okay? When I do the calculation using the mean and the standard error, let's see what we get. So I'm going to clear these. I'm going to now use the new mean of 43.002 plus 2 times the standard error of 4.217. And that gives me 51.436. I will copy, paste, and change that to a negative sign. So my new, according to this calculation, my interval that contains or carries the middle 95% of the data extends from 34.568 out to 51.436. So let's make a comparison. So we agree fairly well on the left endpoint. 34.568 is the calculated left endpoint, and the StatKeys counting method gives us 34.520. That's very good agreement. And on the right here, I've got 51.271, and by our calculation, we had 51.436. So again, very good agreement. So using the mean plus or minus 2 standard errors method is giving us very good agreement to just literally hacking off by counting the lower 2.5% and the upper 2.5%. All right, so what conclusion can we draw? What have we done? We've gone from a sample of size 10 to a sample of size 40. What we can see is our dot plot is just as accurate, right? We're still centered on the mean of 43. But what we're seeing here is that by going from a sample of size 10 to a sample of size 40, we now have extra precision. This method is much more precise. Using larger samples is giving us a method that produces many, many more dots that are closely packed around the true mean value of 43.002. So both methods, because they're using randomness, produce an accurate dot plot. But by going from 10 to samples of size 40, I now have gained extra precision. The standard error has gone from roughly 9 to 4. And you could see that by increasing the size of the sample, we would gain extra precision. So we, by doing randomness, by choosing randomly from our population, we have an accurate method. By choosing larger and larger samples, we will have more and more precise methods. Okay, let's take a look at one more example of this type. I'm going to reset the plot, and I'll just head back to the home page for StatKey. Let's take a look at another problem of this type. For our next problem, we're going to load StatKey. We're going to go back to sampling distributions, this time proportion, and we're going to look at a file called college graduates. This is going to be our new population for study. Now, let's go ahead and take a look at that file and get kind of familiar with what's going on there. So sampling distributions, proportion, and the default is the college graduates file, so we're all set there. Now, what's going on here is we're looking at a population, and within that population we have people that have graduated from college and people that have not. And the parameter that we're interested in is the proportion of people that have graduated from college. And we can see that the current value of that parameter is 0.275. So 27.5% of this population has graduated from college. Now we're going to be sampling from this population, and we should check. We're initially going to want to set our sample size to 50. So let's go ahead and set our sample to size 50. And let's just go ahead and generate a sample or two just to kind of get comfortable with what's going on here. So when we generate one sample, we can see our statistics here. We pulled 50 people at random from this population. 11 of them have graduated from college, and so we're getting a proportion within our sample. This is our p hat, a value of 0.220. We are slightly underestimating the proportion within the population, so we're straying a little bit to the left here. If we generate another sample, we're going to see now amongst our 50, we've got a count of 13, so that gives us a p hat, a proportion within our sample of 0.260. Again, slightly underestimating. Let's generate another sample. Okay, this time we pulled out 50 people at random. 15 of them graduated from college. Now we're slightly oversampling with a p hat of 0.3. Now, so far, these three samples that we've drawn have an average of 0.260. Okay, so this is the procedure. We can go in and generate one sample at a time and build up an idea of how the samples will be drawn from this population and how those underlying p hats will be calculated. What we're really interested, though, is generating thousands of samples at a time. So just like before, I'm going to reset this plot, and I'm going to generate several thousand samples. Let's go to 5,000 samples. Okay, let's take a look at the questions of interest to us. What is the shape of the dot plot? Well, I think we can agree that the shape is bell-shaped. It's a bell-shaped dot plot. What is the mean of the dot plot? Well, the dot plot itself is centered on 0.275, and what we're hoping is that that is a reflection of the population parameter, and in this case, it's an exact match. It's 0.275, and that means that this method is unbiased. It's accurate. It's, even though we're sometimes getting values that are to the left and to the right of the true value of the parameter, on average, we're good. We're at the population parameter of 0.275. Next question is, what is the standard error of the dot plot? We can get that right here. The standard error is 0.064. I'm going to write that down just so I can use that later. Okay. What is the range of the middle 95% of the data? Let's take a look. I can have StatKey do that for me using the two-tail calculator. It's going to carve out the outer 2.5% from the left and the right. It's going to leave me with a middle 95% ranging from 0.160 out to 0.40. So there's my middle 95%. So 95% of the time, my dot is going to land between 0.160 and 0.40. Okay? Now, we're going to compute the middle 95%. We're going to compute the range for the middle 95% using the formula mean plus 2 standard errors. Let's do that calculation. So we're going to grab this mean value of 0.275, that standard error value of 0.064. We're going to go to the scientific calculator. We're going to clear everything out, and now we're going to use the mean of 0.275 plus 2 times the standard error, which in this case is 0.064, and we're getting an endpoint of 0.403. We're going to do the same thing now, except with a minus sign between the terms. When I put the minus sign between the terms, I get a right endpoint of 0.147. So we're going to go back to StatKey, and we're going to compare. StatKey has this left endpoint at 0.160. We calculated using the mean and the standard error of 0.147. StatKey has a right endpoint of 0.40, and using the mean and the standard error method, we got a 0.403. Again, very good agreement. So again, just by concentrating on these two values, the mean and the standard error, we can do nearly as well as StatKey does by just counting the dots, all right? Okay, so we're getting roughly the same answer with a lot less work. Okay, now what we want to do is see the effect of changing our sample size from 50 to 200. What we're hoping to see, just as we did before, is that our method will still be just as accurate. It's still going to have the curve centered on the 0.275, but what we hope is a reduction in the standard error so that our method is actually now significantly more precise. So let's take a look at the effect of changing the sample size to 200 instead. So we go up here, we edit this, we fill in 200 instead. And now just to get familiar with what's going on here, when I generate a sample, I'm now pulling 200 members out of the population. In this case, I'm counting 63 had a college degree, and so I'm getting a proportion, a p-hat of 0.315. Again, when we generate samples one at a time, we're always pulling 200 people out of the population, and we're getting the proportion within that, the p-hat calculated within that sample size of 200. Okay, so let's reset the plot. Now we're going to generate thousands of samples, and we're going to look at our questions, right? Our questions are essentially the same questions as before, right? What is the shape of the dot plot? The shape of the dot plot is still bell-shaped. What is the mean of the dot plot? Well, its mean is the same as the population parameter, right? This is what we hope for, right? Our method is unbiased, and we're getting a mean of 0.275. So even though at times we're creating samples that are off to the left, and we create samples that are off to the right, on the whole, our method is unbiased. It's producing a mean that is reflective of the population parameter, the 0.275. Fantastic. All right, what is the standard error of the dot plot? Well, the dot plot now has a standard error of 0.032. Okay, so we quadrupled our population, our sample size, excuse me. We quadrupled our sample size. We went from 50 samples of size 50 to samples of size 200, and we now see a reduction in our standard error by a factor of 2. Okay? All right. What is the range of the middle 95% of the data? All right, let's have StatKey just count dots for us, and we get a middle range that goes from 0.215 to 0.338. And now we want to calculate that same middle range using our information here, our mean and our standard error. So we're going to take that 0.275 and that 0.032. We're going to go to the scientific calculator. I don't have to change the mean. It's still 0.275, but I will change out this standard error to 0.032 in both of these. And we now find that according to this calculation, our middle 95 should extend from 0.339 to 0.211 to 0.339. So the smaller one here, this is the left endpoint, and that's the right endpoint. So let's compare. When we go back to StatKey, our calculation said that this left endpoint should be around 0.211, and we can see that that agrees nicely with what StatKey has. And our right endpoint we calculated to be 0.339, and StatKey says by counting that it's at 0.338, which again is very, very nice agreement. Okay? Now, what we should notice though, and this is the important thing to notice, by going from a sample of size 50 to a sample of size 200, we have made this 95% window significantly smaller, right? It's narrower, which says that by going from samples of size 50 to samples of size 200, not only is our method accurate, just as accurate, it is actually now more precise. Okay, we are now making more precise statements because our window is narrower, right? Okay, so that's how StatKey can show us how to work with sampling distributions, and hopefully these couple of problems will give you some insight into how to use this this tool. So I just want to summarize what we've seen in our last couple of examples. And I want to look at the effect of the sample size. So as the sample size increases, the variability of sample statistics tends to decrease, and sample statistics tend to be closer to the true value of the population parameter. Now, remember, we're measuring variability through the standard error. And as we saw in our two previous examples, by increasing the sample size, we were able to reduce the standard error, and we were able to make the interval that carries the middle 95% of our samples to be narrower, right? So for large samples, our best estimate is becoming more precise. Okay. Let's take a look at the same phenomenon in some pictures, right? Here are the sampling distributions for the proportion of college graduates for 3 different sample sizes. You can see the sample sizes listed here. There's for n equals 50, n equals 200, and n equals 1,000. And by looking at them together on exactly the same scale, we can see what's happening. When we're choosing samples of size 50, our sampling distribution is wide. In other words, we're going to be seeing some dots out here where the sample proportion is actually quite small, and we'll be seeing some dots over here where the sample proportion is quite large. In other words, we're seeing a lot of variability in those values of p hat that we're calculating. When we move to samples of size 200, we're seeing a lot less variability. We'll still see some underestimation and some overestimation, but in general, the window is much tighter. Finally, by the time we get up to samples of size 1,000, we're still going to see some underestimation on the left and some overestimation on the right, but on the whole, it's much, much tighter. All right, so what we're gaining, in all cases, we're accurate. The center of our dot plot is on the true proportion of 0.275, but what we're gaining by going from samples of size 50 to 200 to 1,000 is precision. We're able to make much, much more precise statements by sampling when we use samples of size 1,000 than we do when we use samples of size 50. Okay, so that concludes that important but rather lengthy section on sampling distributions. In our next section, we want to take up the topic of random sampling. Now remember, the reason to do random sampling is to overcome bias. Random sampling will yield a sampling distribution centered around the population parameter. Non-random samples may be biased, in which case the sampling distribution may be centered around the wrong value. And I think this is best exhibited by studying a specific example. In this example, you'll see that I've got 3 different sampling procedures that are laid out, each of which might appear to be on its face unbiased, but we'll see that 2 of them actually exhibit bias. Let's take a look at that example. So, in this example, we're going to look at the mean word length in the Gettysburg Address. So that's going to be our population. So we imagine we can see the Gettysburg Address in front of us, and every word in the Gettysburg Address is a member of that population. And the population parameter of interest to us is mu, which is the mean word length in the Gettysburg Address. Now, we're going to try to get at that value of mu by sampling. And so we used 3 different sampling methods, and in each case we selected 10 words from the Gettysburg Address and found the mean word length in the sample. That's an X bar. So we're using our X bar, our sample mean, to estimate our population parameter, the mean word length in the Gettysburg Address. Now, here are the 3 different sampling methods. Method A was to simply look at the Gettysburg Address in front of you, circle 10 words, and find your sample that way, right? So it's just like visually scanning the document and just selecting 10 words at what you think is a random way. In method B, I literally wrote out all of the words in the Gettysburg Address as a giant list, and I had random.org just pull 10 words at random from that list. So that would be simple random sampling from all the words in the Gettysburg Address. Method C was a little more obscure. Here you have to imagine removing all the punctuation and all of the spacings between the words and just creating this dense array of letters. So you can still look at the document and you can kind of still see where the words are, but I've kind of reduced all of the spacings. I've taken all the spacings out, all the punctuation out, so I just have this densely packed array of letters. And now I had random.org simply select 10 letters at random from this array of letters. And then the exercise was to take the letter that was selected and reconstitute the word that it's contained in. Okay, hopefully that makes sense. So we're selecting the letter first, and then we're extrapolating back out to the letter or to the word that that letter is contained within. Okay, now I had 52 students, and so I had 52 X bars to report using method A. I had 52 X bars to look at for method B, and I had 52 values of X bar for method C. And here's what the data looked like. Okay, here are the dot plots, and they're arranged from A to B to C down here at the bottom. So we can see that method A, the values for X bar are ranging from an X bar that's around maybe 3.6 up to about 9. We can see for method B, it's shifted to the left, and then for method C, shifted back to the right. We can get the summary statistics over here. Okay, but it turns out that only method B with a mean of 4.225 is right on the population parameter, the mean word length in the Gettysburg Address. In other words, methods A and C are exhibiting bias, and method B is unbiased. It's actually centered on the population parameter. Now, let's talk about the bias that's exhibited in method A. We're simply asking you to look at the Gettysburg Address and circle 10 words in what you think is a random method. Unfortunately, your eye is probably going to be drawn naturally to words that are bigger. You're probably going to avoid the small words and gravitate just visually towards the longer words. And so that might explain the bias in method A. The bias in method C, although we seem to be doing a random procedure by first choosing the letter and then looking at the words that word that encases that letter, unfortunately this method also has a built-in bias towards the bigger words because a longer word contains more letters, and so it is much more likely by this method to select a longer word than a shorter word. Okay, so in other words, a word that's got 10 letters in it has 10 times the chance of being selected as a word that has 1 letter in it. So method C is actually biased towards bigger words, and that's what's shifting the mean in C to longer words. Method A, your eye is drawn to longer words, so that's shifting the mean towards longer words. And in fact, only method B is unbiased. So anytime you're going to be doing sampling, you have to try your very best to understand the possible ways that bias could be entering in to your procedure. And you have to try to avoid that because it is only by having an unbiased procedure that you can expect your results to give you something that's accurate, okay? And it's only by choosing a large sample that you can expect to have something that is precise. Okay, so I want to close off this section 3.1 with just kind of a summary. I just want to summarize what we've done in this section and give you a chance to see kind of a repeat of everything that we've done in kind of one shot. So in summary, I just want to mention that the two watchwords that have been reappearing throughout this section are the words accuracy and precision. So remember, you're trying to do statistical inference. You're trying to use a sample to tell you something about the population. There's a parameter within the population that you are trying to estimate, and you are trying to do that by sampling. There are two things that you would want in your method. You would want an accurate method, and you would want a precise method, all right? So how do we do that? If a sample is chosen randomly, then the best estimate will be an accurate estimate of the parameter of interest. It's not going to be right on the parameter of interest, but we know that on average it will be correct. Okay, so it'll be sometimes to the left, sometimes to the right, but on average it will be correct. So random sampling gives us a best estimate that is accurate. Finally, our best estimate is more and more precise as the sample size increases. So the long and short of it is, if we want accurate and precise estimation of a parameter, we should make sure we rule out all the bias by randomly sampling, and we should make sure that we create a precise estimate by choosing a sample that is large. Okay, that brings an end to section 3.1. I will see you again in a video lecture for section 3.2. Until then, take care and be well.